So this is chapter 6.3 of precalc. All of this, I think, for the most part, is some form of a review of something we did in chapter 5 or something you guys did last year. We changed things up on the first slide here. The first slide has two pieces of information. One piece is the signs of the trig functions. All students take calculus, you got it. All schools torture children. All of those things. We've talked about that many times. Notice that it put also the other little 3 in there as well. So that's kind of nice. What we also have is in the first block here is they're talking about if you have an angle in standard position, that means starts at the origin with your angle starting at the positive x-axis, you will always have a terminal point, all of those things, and you will have an r, x, and a y. R is your hypotenuse, your radius, right, of the circle that would be flying around as you're moving your angle. And what they did is they used x, y's, and r's instead of opposite, hypotenuse, and adjacents. Okay? So it's the same information, but it's based off of this triangle. And this triangle would be someplace here, right? Standard position, theta's at the origin, x is there. Oh, not x is there. Y is there, x, and r. You guys agree with this? So we're not talking about opposite, we're talking about y, we're not talking about adjacent, we're talking about x. Hypotenuse is r. Okay? Nothing new. I can rotate this into any one of the 4 quadrants. The only thing that'll change is the signs on x and y. R is always positive. Hypotenuse is always positive. I'm recording. Reference angles, guys. This is nothing new either. We've had reference angles before. Now they're kind of putting it to another definition here. They're using theta, and then using theta with a bar over it. The one with the bar over it is the reference angle. And it's from standard position, the reference angle associated with theta is the acute angle formed by the terminal side of theta and the x-axis. In other words, like I have been saying, the reference angle is the angle that is from where you stop to the quickest x-axis. The leftovers, or how much more it takes to get you to the x-axis. Either way you want to look at it. And again, there are several ways that we have done this. We've done this with a graphical approach, by graphing the angle. We've also subtracted or added 360 or 2 pi by finding coterminal angles first. Figuring how many times am I going around the circle and then terminating someplace. It's a couple different things. So the first problem there, I realize that's a little bit on the smaller side, is 5 pi over 3. So 5 pi over 3, what is the reference angle? So we'll do this a couple different ways. The first way, I'll do a totally graphical approach here. So I start to make my graph. I'm going to change colors, and I messed this up first hour because I ended up counting the wrong colored line. But if I was to cut pies into 3s, I'd have one here, have one here, and have one there, right? And then I would have here, here, and here. Yeah. Each pie gets cut into 3 pieces. The thing about it is how many of them I move. How many pies over 3 do I have? What's the number? 5. So here's 1, 2, 3, 4, 5. So I actually stop here. So then all you have to do is ask yourself, what would it take to get back to the x-axis? Another step of pi over 3, or 60 if we were in degrees, but we're in radians. So guys, the reference angle is pi over 3. I messed up first hour because I went like this. I went 1, 2, 3, 4, 5. I end up actually getting the same answer, Because if I stop here, the quickest x-axis is the negative x-axis, which is still one step backwards. It's still pi over 3. Remember, reference angles are always positive. They always reference the first quadrant. And in the first quadrant, everything is positive.
Mm-hmm.
We like things to be positive.
Yeah.
We like positive people.
Yeah.
We like happy people.
Yeah.
Because it makes us happy when we see other people happy. Now, the other approach, guys, the other approach, could I have taken 5 pi over 3 and said, hey, wait a minute, isn't that just pi plus 2 pi over 3? Because how many times does 3 go into 5? One time with how many leftovers? 2. And so, wait a minute, if I was to do this, I still have to put a little bit of graphical approach to it. I go, hey, I move 1 pi, and then go 1, 2. There I am. 2/3 of a pi more still has pi over 3 associated with it. We have done this before. Yes, I said today's lesson is pretty much a review. Do the same thing with 870. So you could graph 870, but to graph 870, I think it might be easier to find its coterminal angles. And to find coterminal angles, can't I just keep subtracting what from it? 360. And so, minus 360, is that what would that be?
Minus 360 twice is 1.
So that would be a 10 and a 5, 10. That's not enough. Do another 360, because I can keep going. What does this end up being? 150. I have a coterminal angle at 150. Hey, that's not too bad. There's 150. Boom, right there. There I am. What's the leftovers? 30 degrees. 30 degrees is the reference to 150, which is also the reference to 870 degrees. What did it mean when I subtracted 360 and subtracted 360, guys?
Go around twice.
I'm starting here at 0 and going 1, 2, and then going the additional 150 to there. I'm just getting rid of the extra spinning.
Don't want to get busy.
Okay? Makes sense. We've done this before. Hopefully it's starting to really sink in. Can I turn the page, guys? So, why is this all important? Why do I care about the reference angles? Good, I like positive things. 2, what I also like. I like to evaluate sine, cosine, and tangent for anything, for any of the angles. And so therefore, by finding reference angles, since they terminate in the same spot, they have the same values, I can use it to my advantage to evaluate sine, cosine, tangent, and their reciprocal functions of angles bigger than or less than 360. Or from 0 to 360. So outside of that. Very large, very small angles. You got a couple things going for you here. There are a couple things that are going to go for us today is the fact that all of our angles are going to reference something in the first quadrant that you know. Which means it's going to be of a 30, 45, 60, 90, something of those. You're going to only have those types of angles or their radian measures. So therefore, you don't have to worry about a sine of 10 because anybody can take their calculator out. You can do this. You can put sine of 240 on your calculator. It'll tell you an answer. But the biggest thing here is we're going to find a reference angle, but then also have to make sure that we are referencing it in the right quadrant because we have to acknowledge that this is going to not always be in the first quadrant, so it might be negative. So you can follow the steps that the book uses. You've got to find a reference angle sometimes by using coterminal angles. You need to also acknowledge that the sign is going to be there, so there might be a negative, and then just evaluate. So sine of 240. We all know where 240 is. If not, we can also use some of our other techniques by adding or subtracting 360 from this. But where's 240 about? What quadrant? It's in the third quadrant. So someplace down there. What would the sign be of sine 240? You don't even need to know the value right now. You know the sign will be positive or negative? Negative. Sign is negative in the third quadrant. Okay. You should know that. But then what we're going to do is say, what is that reference angle then? What's the leftovers? If I'm at 240, what would it take to get back to the x-axis?
60.
It would take 60 because you would have to go from 0 to 180 and then go a little bit more. And that little bit more would be 240 minus the 180, which is 60. So what does this mean? It means that sine of 240 is equal to the sine of 60, but it's also negative. Because remember, first quadrant's always positive, so therefore I'm going to take the sign and put it up front. And we should all know, actually from the top of our head, what's the sine of 60? Square root of 3 over 2. So the answer is negative square root of 3 over 2. Can you do the exact same thing with cotangent? I would hope so. I don't like cotangent. So change it to what?
1 over 10.
So it's 1 over the tangent of 495. They are the same. We also then can say, wait a minute, I don't like 495. I'm going to find a coterminal angle. What are you going to do? Subtract 360. If I subtract 360, I get 1 over the tangent of 135. So the cotangent of 495 is the same thing as tangent 1 over the tangent of 495, which is the same as 1 over the tangent of 135. And then, if anything, you draw yourself a little graph. 135 is there. Has a reference angle of 45. That means that it's also equal to 1 over tangent of 45. Or is it? Bless you. It needs to be negative because tangent in the second quadrant is negative. And we all should know what tangent of 45 is. 1. So therefore, it's 1 over negative 1, which is negative 1. Could you have put these things into your calculator and got a decimal answer? Yes. The tangent of, or cotangent of 495 would give you an exact answer of negative 1. That's fine. But square root of 3 over 2, or the negative square root of 3 over 2, would have been a decimal answer. We wouldn't accept that because I want exactness.
But you can still not like
But you still could potentially help check to make sure you're doing things correctly. You guys should be able to do all of this without a calculator. I should be able to take the calculators away on the next quiz. And nobody should cry about it.
Top is already
I have
cracked.
to do 2 plus 2.
Okay? Questions? If you can do this with the degrees, then you should be able to do this with radians. Try these on your own. Sine of 16 pi over 3. I think the most efficient way to do this, we could, again, graph it like we did last time, cutting pi's into 3 and counting 16 of them. Or, how many times does 3 go into 16? So it would be 5 pi plus pi over 3. Do you guys remember this? Now, hey, I was actually kind of thought of this during the first hour. Do you guys remember that there's a trig identity for that? That when you have a sine or a cosine of 2 angles being added, it's like sine, sine, cosine, cosine?
No.
Sine,
Or
sine, cosine, sine, cosine, cosine, sine, sine, sine.
that's the kind of something like that. So we'll learn that pretty soon here. But what we have here then is we can draw a picture. 1, 2, 3, 4, 5, and a little bit more, and that little bit more happened to be pi over 3. So we have a reference angle pi over 3, but sine in the third quadrant is, so it's not just sine of pi over 3, it's a negative sine of pi over 3, and sine of pi over 3 is square root of 3 over 2 negative, which is a negative square root of 3 over 2. We're not switching from radians to degrees. We're evaluating sine of pi over 3. Any questions? So it's really not so bad. I don't like secant. Change it to cosine. I don't like this either. Here's a cool thing. How many people recognize that secant or cosine actually is even? And if it's even, the negative sign will go away. So therefore, it ends up being 1 over cosine of pi over 4. And what is cosine of pi over 4? Square root of 2 over 2, which is 2 over square root of 2. Guys, the other day, we were given answers like this when we had to use our triangle. And I said at that time, when we're just trying to list the sine, cosine, tangent of theta, this was okay. Now, we're trying to evaluate and give exact answers. Is this okay? No. This is not okay, so fix it. So 2 square root of 2 over 2 cancels out, and it is square root of 2. We're bringing back this slide. Same exact one you guys saw in chapter 5. It's the exact same. I just said that. Same exact thing. We don't need to remember all of these, do we? You only need to remember the first one, because you can build the others. If you write it, you can build it, is what they say. So I'm going to move on. Why? Why did we bring this back up? Because of that question on the quiz that you guys didn't like. Write one trig function in terms of the other. They're bringing it back again. So again, it's all kind of review today. Can you write sine of theta in terms of cosine theta?
Yeah.
So, how do we do this? You start off with sine of theta. Some people actually did this type of problem the other way. Exactly right, but they put the second one in terms of the first. I want the first one in terms of the second. I don't want sine anymore, I want cosine. So, I need to kind of sidebar on this one. I need to say, wait a minute, is there a link between sine and cosine? And then it happens to be sine squared theta plus cosine squared theta is equal to 1. So it means if I solve for sine squared theta is equal to 1 minus cosine squared theta, and then take the square root. There it is. Now, notice that this first problem doesn't talk about quadrants. And if it doesn't talk about quadrants, we're going to assume what? First quadrant. So we know everything's positive. So guess what? Sine of theta is the same thing as 1 square root of 1 minus cosine squared theta. Done. That, if it wasn't in first quadrant, so say if this was in third quadrant, you would have to put the negative on it, because in third quadrant, sine would be negative.
Would you put the negative on the sine or the square root?
No, you have to put it on front of the square root. Because you want this thing to be negative at the end. Or guarantee it. The second one starts off with tangent theta. We know some things about tangent. Tangent is what? Sine over cosine. I only want this in terms of sine, but in the second quadrant. And sine in second quadrant is positive. Wait a minute, sine. But tangent is negative. So we're going to have to take in consideration there at the end that the overall answer better be negative. I did want to get rid of cosine now. Using the same logic that we solved for cosine before, can I use the same thing for cosine? Or vice versa? Without having to solve it, what would it be? 1 minus sine squared theta. Now, here's the problem. In third quadrant, sine itself is positive. So the top will be positive. When you're squaring any number and taking the square root, it will also be positive. So this whole thing is going to be positive no matter what we do in second quadrant. So therefore, I need to put a negative in there to guarantee I have negatives because tangent was negative. The square root is fine on the bottom for this. I'll be okay with that. No, because tangent itself will come out as negative because you're in second quadrant. It's not there until you put the angle in or evaluate it. Guys, this one goes back to, hey, if I give you one of the functions, can you find the other 5? Not that big of a deal. The biggest thing you need to remember to do is draw your angle. You're talking about an angle in third quadrant. There's theta. Tangent would be opposite over hypotenuse. Here's the thing. 2 and 3 actually are both what? Negative. And using Pythagorean's theorem, can you solve for r? 3 squared plus 2 squared is the square root of 13. At this point, can you tell me cosine of theta? Could you tell me sine? Could you tell me cotangent? All of those. Okay? I'm not doing part B either. I'm not finishing this problem. I think that's pretty straightforward. We've done that already. Last one is talking about area of triangles. Here's the cool thing. As long as I use that formula and realize that A and B are just the sides of the, with the angle included in the middle, like our picture here, where we have 3 and 10, but the angle between them is the one that's included. You can find the area of this triangle just by saying, hey, 1/2 AB sine theta. Done. Which means that this is 1/2 3 times 10 times sine of 120. Make sure that you're in degrees on this one. If it's in radians, make sure you're in radian mode. But you shouldn't need it. What's half of 3 times 10? So it's 15 sine of 120. I don't like 120, so that's sine of 60 because it's a reference angle. 120 is in the second quadrant. Sine is positive. Therefore, I don't need to worry about sines because sine of 60 is also positive. And what's the sine of 60? So the answer is 15 square root of 3 over 2 units squared. Done. It could be that easy, guys. Just make sure that if you're in radians, you're in radians. If you're in degrees, you're in degrees. All of that stuff. Everything should be hunky-dory. Okay? Not wonky. Homework, page 501, 1 through 56, every 5. Have fun counting, guys. Have a great day.